I don't have the best setup in the world here, but I'm going to make do. So this is where you go to find my folder on various energy ideas. And then when you go there, you'll get a listing, and these are the items here. The RMS zip has various files, and one of which is version 64E and 64A. Then there's also RMS text, and there are a few other files in there. In fact, I'll show you what files are in there. Whoops. Okay, if I can, here we go. So the files that are in there is a screenshot of a spark gap, how to turn off this analog computer power amplifier. Then there's the version 65, and then here's version 64E. 64A is an older version. I just have that in there for reference. And then various screenshots of version 65. The RMS current of a battery pack, 74 volts, and then another battery pack to compare with, and then the node voltages measured in reference to ground and various points in the circuit, and then the schematic. No, I don't have the schematic. Oh, that's right, I don't. So I just assume that you'll have microcap and you can open up the file and see it for yourself. Now, how to turn off the analog computer, that's interesting. Maybe I should show you the schematic first. So let's see. Let's go over to here. Whoops. Wrong one. Here we go. I was in the right place. Okay, let's back away. Alright, let's see. Nope, wrong way. Okay, now this, first of all, this is the spark gap macro for microcap simulator. And it has a parameter list at the top, which is your variables. So you have your breakdown voltage of 90 volts, your arcing voltage of 10 volts, so it drops to 10 once it starts to arc. Then you have your sustaining current of half an ampere. Let's see, what's the definition here? Sustaining current under which the arc is stopped. Not quite sure I know what that means. Then you have negative resistance to make sure the spark gap behaves properly when it is arcing. And then you have LPL. What's LPL? Lead electrode inductance. So the two electrodes that are at either end of the neon bulb, because I take this to be a neon bulb, they call it a spark gap, but the voltage breakdown of 90 volts, that's pretty close to being a neon bulb. So it's a specialized version of a spark gap. A spark gap might have a voltage breakdown of 1,000 volts, which is not this, obviously. So I'm pretty sure this is a neon bulb they patterned this off of. Now the lead inductance is the inductance of the two electrodes, and that's at 130 nanohenries. Now the resistance of those two electrodes is 2,000 ohms. RPL, lead electrode resistance. Now the capacitance in parallel, the gap capacitance, CPAR is the gap capacitance, is 1 picofarad. And then the arc capacitance, when it's struck, is 3 picofarads, so it goes up slightly. Now that's the features of a spark gap, and I use a spark gap for two purposes. One is to provide negative resistance in parallel with my capacitors of Eric Dollard's analog computer, and then it becomes over unity in the sense, well, it becomes exacerbated over unity in the sense that you can shrink down the size of the circuit, because Eric Dollard's analog computer in longitudinal Magneto-Dielectic mode by itself is an over unity device, but you have to get it up really big enough to take up the size of a room or a warehouse, and that's not exactly convenient or cost effective. So in order to shrink it down, I have to put negative resistance into the capacitors of each module that's daisy chained, and then I get to shrink it down. I might have to increase the frequency to compensate, but at least it works. I can shrink it down and make it work. The other point of using spark gaps, though, is to create staccato wedges. In other words, without the use of spark gaps, if you just use caps and coils, you'll get an over-unity device that wants to go to infinite gain and fry itself. But if you manage to put in spark gaps in the right places, not only can you enhance your surge, your escalation to infinity, so that you can shrink the circuit down and get the same effect without having to utilize so much capacitance and so much inductance to get the same effect. Not only can you scale it down, but you can also chop it so that the surges expand away from the midline on your oscilloscope tracing and then collapse. And then they arc out and collapse, at a hyperbolic curve, but then they collapse suddenly almost vertically straight into the midline of your oscilloscope tracing. And that creates pulses of surges. And those pulses, very often the story goes that UFOs pulse. And this is what this circuit does. I can get it to pulse and maintain a semblance, an RMS average semblance of a certain energy level that averages out, and then I can regulate the output. And then, of course, if the pulses are regulated, which sometimes they're not, sometimes the circuit wants to be random in its output, but if it's regulated, it wouldn't be too hard to use pulse width modulation digital technique to convert these triangular waves that are at the basis of, usually at the basis of this circuit, into sine waves to power a motor. But if you're not going to do that, you could recharge batteries in, let's say, an electric car or in a home situation. So you could scale down your solar panel on the roof of your home to a postage stamp, literally the end of my thumb, to power this circuit. And this circuit uses electrical reactance to recycle its reactive power and convert the excess using power factor correction into real energy, useful energy, and now you've got yourself a magnification of power seemingly. But in actuality, it's a magnification per same unit time, because you've shrunken down the unit of time in which your allotted energy is recycling, so that it looks like you've increased your energy when all you've done is shrunken the time frame of recycling your energy. So if you have a one-pass situation in which a flashlight circuit, and the way we use our energy in our homes, the energy comes from the source, let's say on the left-hand side, it goes to the home on the right-hand side, and then it goes back to the grid. And it's a one-time use. But if we recycle our energy, there's a simple example of putting a capacitor in between the source and an inductive load. And it starts to go around, or oscillate actually this way. So instead of going to the grid, it goes to the capacitor in between our mains utility meter and our motor load, our coil load. It oscillates at a shorter distance, and it never goes to the meter, let's say 99% of it, and so we recycle 99% of it and still get to use the voltage coming in from the utility grid to keep our voltage the same, 120 volts, 60 cycles per second. But the amperage never goes back, 99% of it never goes back to the meter. It just ricochets off this capacitor in between the meter and our motor load. But that is only 99% recycling, which means the duration of time, maybe time is not the best way to explain it. All I know is it's recycling. But you can increase the factor of recycling beyond 99%. And I take it to ridiculous levels, because what happens is it becomes a avalanche effect. It snowballs. Once you get past a certain point, it just wants to escalate the rate at which it recycles, so that now you've got a problem to regulate this thing, or else it'll blow up in your face. So I just use a standard spark gap macro from Microcap software to enhance the circuit. Now this is the circuit, and it has, let's zoom in here. It has one module here, LMD module, and another one here, fully scaled, separated by transformers. And then we have a mini module on the two ends. So it's like we got 4 modules, but they're not really. It's like 2 full modules and then 2 halves. And this is an artificial, a ballast load of an inductor of, how much do I have here? 1 microhenry inductor here, and then a 2 microfarad capacitor in series. But then I have a capacitor down here of 100 nanofarads, a capacitor up here of 100 nanofarads, and then a spark gap, or I call it NB for neon bulb, putting negative resistance in parallel with this spark gap. So I could go into the spark gap in the simulator and put in negative resistance in parallel negative resistance. You know, it'll already have 100 milliohms, or somewhere between 10 and 100 milliohms of positive series resistance. But if I put in negative parallel resistance, it's the same as putting a spark gap on the outside of the capacitor in parallel with that capacitor. Now I have a lot of little resistors of 100, 101 or 99 milliohms, and that represents a very bad solder joint. So I want realism as much as possible, so I put in solder joint resistances. And I doubled my transformer. Usually use radio choke coils, but then you short it out between your modules. That's the way Eric Dollar does it. I learned not to short them out unless I want to enhance it, so then I put a capacitor short between 2 modules. And I use the square root of 10 because the capacitance in this module is 100 nanofarads on each capacitor. Then the next one to the right is 10 times more, and so on, 10 times more and 10 times more. So the capacitor in between the modules, I use the square root of 10, and each one is 10 times more. So this one is 316.22 nanofarads, and then the next one is 31.624 microfarads. Is that micro? What happened here? Oh, here's the micro. Yeah, so this was 316 nanofarads, and then it was 3 microfarads, roughly speaking, and then 31. And notice I slightly vary them. So there's a problem with this microcap simulator in that in its attempt to approximate the calculation of what your circuit is doing over time, when it does a transient analysis, which is the kind of analysis I use, it gets flubbed up. You get matrix as singular errors, and all it means is it uses matrix algebra in order to approximate the calculation of what your circuit is doing. And in matrix algebra, there's something called your determinant, and it's basically a 2 by 2 array of various values that you derive from your various polynomials that you're simultaneously trying to solve for. And if, I believe they're the coefficients of the polynomials, but be that as it may, when the total determinant of the matrix is 0, you cannot invert it, and then you get this matrix as singular error. So what I've learned to do by trial and error is to put in resistances of slightly different resistances throughout the circuit, and then go further and vary the values of all the components slightly. So this capacitor is 10.001 microfarads, but the one below it is 10.002 microfarads. And then I go into the capacitor and I change its parameters. So remember I showed you the parameters? This is the default parameters of every spark gap. But I go into every single one and slightly vary each of these parameters so that no 2 spark gaps has exactly the same parameters. And I always use the same value of 1/10 of 1% to vary each parameter of each component. That way I help to mitigate or eliminate matrix is singular errors. And I do it on everything, even, okay, so what I do here is I build up voltage. That's all his analog computer is good for, is building up a humongous voltage. And in LT Spice, you can't get away with this. they'll give you a different kind of error. They'll say floating node, meaning all of these nodes that I'm able to amass voltage of negative 4.744 gigavolts on the left side of this C12 capacitor. You can't get away with doing that in LT-Spice. They won't let you. They'll give you floating node error saying, oh, you've got to ground out this node over here to bleed that out to ground. Now, why would I want to do that when the whole point of this over unity experiment is to build up voltage, not bleed it out and prevent it from building up? Now, if we go to our input, which is a sine wave generator, see the node associated with ground here is 0. And then on the other side of the sine wave generator, it's a fraction of a femtovolt. It's 0.001 femtovolts, which is basically negative 1 attovolts. So it shows you how little voltage is building up near the input. But everywhere else, it's building up like crazy. Sorry for the shaky hand, I'm old. So what I've learned to do in LT-Spice, if they force me with a fatal error message, is I don't use a resistor between the circuit and ground. I use a capacitor of 10 picofarads, and that actually boosts my voltage buildup and prevents it from bleeding out because I'm using an oscillating circuit. The blocking capacitor of 10 picofarads is perfect of a low farad value, of a low capacitance value is perfect for dumping, not only dumping half of its energy out of the circuit into ground, but half of it is bounced back in. And it dumps it very readily because it's a low capacitance. Rather than storing, it immediately discharges because it can't hold on to much, and so it's able to act like a mirror, and just, but also like a prism, in that it allows for some of the energy to leave the circuit, but some of it to build up. And LT-Spice will accept that. The problem with that is that it makes the energy buildup in here escalate so fast that I can't regulate it. It literally blows up in my face. In fact, I have one version of this circuit in which literally I have the time frame for the transient analysis is 1e to the negative 100. And it literally goes to infinite gain and shuts down because it can't go any further. And you're stuck with an explosion in your face that is instantaneous. You can't even find out how fast it goes. It's so fast. So I don't like LT-Spice for that reason. I mean, it was okay for simulating Joseph Newman's device and figure out that he had a higher frequency than what he professed. You know, the thing rotates maybe 30 times a second, or was it 30 times a minute? Yeah, it might have been the rotation speed. I can't remember, but it was very slow. And so I upped it to 100,000 rotations per second, and it became over unity. So he says build it bigger and it'll become over unity, and that's a lie. What he really should have said, if he wanted to be honest with the public, he would have said make it somehow oscillate faster. But you can't rotate it faster than what mechanically there are limits to. So what he did, he replaced the permanent magnet in this rotor in the center with canisters of helium in PVC sewer pipe, capped them off, and then put an open coil around each one. And the voltage of the surrounding coil inspired the helium to emit electromagnetic vibrations of a very high frequency. And that, in combination with the low frequency coming from the commutator fed by his battery pack, created a slightly complex waveform, but of a higher net frequency, and that created over unity. So I went from that simulation model to this, well, actually to something else, not this. And that something else is called my reactive motor, and you can get it from is.gd/reactive motor. But it's not exactly buildable. I need something buildable. And this is buildable. So it may be dangerous. That's a different consideration. Because, you know, gigavolts is going to want to find a path to ground, and most likely will take the nearby object of your body, and you could have a problem. You may die. So this is definitely a dangerous circuit, but it is buildable, and it just might work. with off-the-shelf parts. Now the transformers, I doubled them. So not only do the capacitors go up in value from left to right, but the transformers go up in value between any two daisy chain modules, and I repeat it. But only one, where's my finger? Only one goes up. So this one on the left, and they're in parallel, they're connected in parallel. And then they're shorted with this capacitor on one side. So this left transformer, the left coil is 10 microhenries, but the right coil is 10 millihenries, 1,000 times more inductance, and there's a coupling coefficient of 0.7. Now here, the coupling coefficient is the same, but I make the inductances the same. Both the left-hand coil and the right-hand coil is 1 millihenry. And then I just repeat that between each, bordering between each module. Now these connections are parallel, so the left coil is connected to the left coil of the right transformer, the left coil of the left transformer. So I don't short out the transformers with resistors, only with capacitors. So I keep everything isolated. The modules have to be isolated from each other. When Eric Dollard shows you how he does his analog computer from the 1980s, he shorts it out with a piece of wire, and he's killing the voltage buildup. And yet you still get voltage buildup, but not as much as this. So it's important not to short out your modules with a straight through connection. You have to block it with a blocking capacitor. And then you get even more buildup than before, rather than bleed out. Because the easiest way to turn off this circuit, and the only way that I know of, because it's going to always be on, is you take away, where's my finger? You take away, where's my finger? You take away the coupling. In other words, you take out the, let's say this is an iron bar, an iron center to this transformer. You take it out. You take it out of here, and you separate the coils. So you slide, so you have to wrap these coils on separate coils possibly, and slide out one from the other to bring the coupling coefficient down to 0. And then this thing stops itself. Instead of escalating, thermodynamics takes over, and all the various resistances will eat away at all of your voltage buildup and make it go away and kill the circuit, basically. And you'll be left with a little flutter of energy inside here that it won't amount to anything. And you'll be able to turn it off. That's the only way I know of. And then you bring back the inductive coupling between the left-hand coil of each transformer and the right-hand coil of each transformer, and then the thing just turns on and wants to escalate to oblivion. Also, provided you put some energy in here. Now, where is it? The sine wave generator, I've got a switch here that turns off after 1 femtosecond. So for a mere single femtosecond, you know, a femto is 1,000 times shorter duration than a pico, and a pico is 1,000 times shorter duration than a nano, and a nano is 1,000 times shorter duration than a micro, and a micro is 1,000 times shorter in duration than a milli, and a milli is 1,000 times shorter in duration than a single second. So we've got 1 e to the negative 15 seconds of the switches open in the very beginning to allow the sine wave as it to give just a portion of its curvature, which is, you know, nearly vertical, because the frequency is of the sine wave is 300 teracycles per second of frequency of 1 microvolt. And so the slope of that sine wave as it rises, because this in the program here, I guess it always starts at baseline and then rises. So if you can center, I guess, do the same thing, or run it a little longer but then cut it off. You know, you want to make sure you cut it off, because otherwise you're going to hamper the ability for this circuit to build up voltage. And also you want to keep the voltage down. That's the other trick. You got to keep the voltage input down. The window of opportunity is a minimum of 1 microvolt and a maximum of about 10 volts. And if you keep it in that window, and then also use a snap switch so that you only energize this momentarily and then let it build up on its own, then it'll go through the roof, and which is what you want to do. Now, since all it does is build up voltage, we have to artificially bleed off this voltage in order to create a flow of current. And then the pathway for that flow of current is where you place your load. Now, I tried various places, and I found that in the midline between the two core LMD modules is the best place to do it, off of the gap between the two transformers. So that means I'm taking it off the capacitor here, or the left-hand side of the capacitor up on the opposite side, because these are isolated from each other with the transformer in between. I have to take it on the left-hand side because I don't use a capacitor to short out the two parallel transformers. But on the bottom, I do, and so it's pretty much equivalent to taking it off of the left side of the capacitor, which is the left side of the two parallel transformers up here. And this is the midline between the two core modules. And I only need to put a spark gap on one side of the circuit, so I do it on the top side, injecting negative resistance into parallel with the top side capacitors. I don't have to do it on the bottom side capacitors. But now the bleed off, I send it to ground, and I have a switch, another switch for each bleed off, but this time I do things backwards. The switch is open. In other words, there's no pathway to ground for the first 10 picoseconds. And then after that, the switch is engaged for the rest of the simulation, allowing bleed off. So I allow voltage to build up for the first 10 picoseconds of simulation, and then from that point forward I can bleed it all off, because now it's like starting a fire. If you're starting a fire using a single match, you can't light a log. There's no way. You gotta light tinder, grass, dry grass, tinder, it's called tinder. And then you build up, you add in tiny twigs, and then larger twigs, and then finally you can add in logs. It takes a while. Sorry for the background noise. I'm living next door to Walmart here, right where they do their deliveries. So you build your way up to a roaring bonfire gradually, and that's what I have to do, because I'm only given this 1 microvolt for a femto of a second. So I have to allow 10 picofarads to pass before I can begin to make use of this power. And yet, despite the fact that I wait that long, from 10 picoseconds further in time, the thing still wants to escalate. But it'll escalate to a limit based on the size of the capacitance and the size of the inductance in my modules. They will determine to what degree it rises to. And it'll surge in the beginning and then die down. Oh my God. It'll die down and to a average level. And then you've got your average output. But at first it'll surge, and it'll surge kind of high. So you gotta kind of not use this right away, because it'll give you a jolt of power more than what you need. But let's see. So what I do is now I put batteries, because I don't want to, since I don't know how to deal with pulse width modulation. I know in general you use op amps or something similar, but how are they going to deal with high voltages and high currents? I don't know. So I figured I'll do the safe thing to do is just recharge batteries. So I got a ring of dead batteries. Where's my finger? I gotta have a pointer here. I don't have a pen as a pointer. I'm gonna have to use my finger. Where's my finger? Okay. So I use an outer ring of dead batteries of 1 femtovolt. And that helps act as ballast. And then I have a short of 1 milliohm, which is less than my other solder joints of 100 milliohms. So I have this short here to, what it does is it diminishes voltage. The amperage stays the same that I'm bleeding out, but the voltage drops because of this reduced resistance short. And that helps, what does that do? That helps increase the ratio proportionality between voltage and amperage. So with solder joints that are all the same of 100 milliohms, I get a gain of amperage to voltage of 10 to 1. So the units of amps versus the units of volts is 10 to 1. Well, I want a bigger gain than that, and so I have this short of 1 milliohm, and that gives me a gain, I think, of around 1,000 to 1, if I'm not mistaken. The the amps unit, the units of amps to units of volts is 1,000 to 1. If I'm not mistaken, I think my memory serves me. We'll see in a second, I guess, if if I recorded correctly. But that's only along the short. Now, where's my finger? Okay. Now, in between, I have another loop here of batteries, but these are batteries with normal voltage that I have charged. So this battery over here, V quad 1, is 72 volts, and this one over on the right-hand side, V quad 2, is also 72 volts. And it has the correct voltage. I believe it has the correct voltage, if I'm not mistaken. When you measure the battery, the node voltages don't look right. Oh, no, they do. Let's see. Let's zoom in here. So that's 200 volts negative versus 130 volts negative. So the difference between 200 and 130 is about 70. Yeah, that's 72 volts. So RMS, there's a surge in the beginning, but if you do an RMS rating on the voltage of these quad batteries, it averages pretty much to 72 volts. So you get this slight surge in the beginning, and then it tapers off because they're spikes, basically. And so they're oscillatory spikes. And so the battery gets massaged. It charges and it discharges alternately in so far as the spikes are concerned, wafting past the battery in both directions alternately. And that helps massage the battery, condition it. I call it massaging, but conditioning. But what I found in the past, what happens when you have an oscillating circuit giving raw energy to a battery, what happens is usually you get slightly more current goes back to the battery to recharge it than what discharges it. And so you end up trickle charging the battery. So this is good. This is like a trickle charge system when you use raw oscillating energy to feed into a battery rather than forcing DC current straight into it. And you run the risk of reverse polarizing the battery if you do too much, if you supercharge your battery too often or too much. But this trickle charge method of using oscillating waves is much safer for the battery. It conditions it and it slowly charges it, but it's all free current. Now the current is humongous though. And I have it, it's actually, in this circuit example, I managed to get it slightly higher than it should be. So now let's go to, and also this, for some reason, because, where am I? Because of these spark gaps are on the top side, this bleed off actually has less energy than the bottom bleed off. Where is it? Where are you? Than the bottom bleed off. V quad 3 and 4 and 4. The amperage is less. So they're different, and you can then vary. You could probably vary how you pulse your batteries by switching back and forth between the top bleed off and the bottom bleed off, and then regulate the time you spend spending the duty cycle you spend up here using this energy to charge your batteries versus the energy down here. You could swap your batteries back and forth, or swap which side of the circuit you use to charge your batteries, and then you could create an average that's more precise to what you want to feed your circuit. So that's the way I look at it. You use one side should be less than the amperage you want to feed your battery, and then the other side, the bottom side, is more, and then you create a duty cycle of each so that you get the right average to recharge your batteries. Now let's look at some values here. This is, if I can back up here, let's see, this is the current for V quad 1. Now if you look at the arch here, it arches up here at somewhere in the vicinity of 750 amps. 750 amps. Now this is RMS, so I'm averaging out all the spikes. And so in the very beginning, it's a big surge, and then it wants to flatten out. And then it goes up to another surge, which is just below 900 amps. Now these steps eventually will flatten out, and I just can't do a long enough simulation because my laptop is, I mean, this takes literally gigabytes of space on my hard drive to store the data file for this 10 nanosecond simulation. So I can't do a proper assessment to confirm what does this average out to RMS eventually after, let's say, half a second or 100 milliseconds. I'm having to ask somebody else in another part of the planet to do this simulation for me on my behalf, and he hasn't been able to do it yet. We haven't been able to work it out. But this is all I can do. But I've done, this is 64A. Where is it? This is this is version 65, excuse me. But 64E is a smaller circuit, smaller capacitances, smaller inductances, 1,000 times less of each. And I was able to see how this circuit behaves in a quicker span of time because the output was reduced and the frequency was, or let's say the time frame of how long it takes to reach maximum before it then starts to subside and even out, was much sooner rather than later. And so within the limitations of my laptop, I was able to see how the circuit behaves on a smaller scale of nanoamps. So it wasn't exactly obviously something I want to use in practical life, but I was able to get a foreshadowing of how this circuit works. So I have a pretty strong indication that the circuit is giving me what I want. I just can't confirm exactly how much it's giving me. So it's going to be something less than 800 amps or 1,000 amps. It's going to be something less than that. Hopefully, 200 amps for an EV to accelerate up a hill versus 50 amps cruising speed on the freeway, and then somewhere in between that. That's the kind of ballpark window of amperage we want to be feeding our electric motors in our electric car as it's driving along. So we're using a postage-sized solar panel to feed the circuit, yet the outcome is in the dozens of watts, dozens of watts we're recycling our energy so that we can scale down our footprint of a solar panel to practically nothing. Practically nothing. Now, what's this next image? This is V quad 3. Now, see, V quad 3 is less than V quad 1. V quad 1, this first surge is at It's 750 750 amps. But V quad 3, which is up on the top side of the circuit, now it's around the other way around. V quad 1 is at the top of the circuit. V quad 3 is at the bottom of the circuit. And now we're approaching 20,000 amps for just the first surge alone. And then the second surge, there is close to 30,000 amps. So obviously it's too much, but if the other version is slightly less than what we need, it may not be. This might have to be tailored. The circuit might have to be slightly tailored. So let's see if I can expand this. Where's my cursor? So if I want to decrease all my capacitances slightly, not 1,000 times less like in 64E, but in this 65 version, if I slightly diminish the capacitances and the inductances, then I'll get slightly less output and hopefully be within the target range of what would be practical for this EV scenario. But right now I just have it close, in the vicinity, in the ballpark. And that's good enough for me. I don't have to fine-tune this because this is just a simulation to make sure I know what I'm dealing with. So if I was building this in the real world, I would start small with a small size circuit, and then gradually each model would be slightly larger in capacitance and inductance, still keeping to the same frequency of the sine wave input. Just increase the parameters of capacitances and inductances to increase my power level. So let's see if I have any other images. Now this is this is 64. Oh, B. This is B. But it's kind of similar to 64E because it shows a surge. It's very small. This is, it's not the same as 64E, but negative e to the negative 29. So you get the surge in the beginning, and it oscillates, and then it flattens out, and it evens out to another value, but it's still above 0. Here's 0 is down here. So that's what I suspect happens. So that's all for now. Thank you very much.